Hello everyone, I'm Adrian, and today I'll present our paper, Exact Langevin Dynamics with Stochastic Gradients. My collaborator is Vincent Fortoin. You can see him on the left. Check out the description below for links to the paper, references and slides. Suppose you wake up one day and decide to do posterior inference in a Bayesian neural network, or any parametric model with a large dataset. Your thought process might go somewhat like this. HMC is great. It reaches the typical set of the target distribution quickly and then explores it efficiently. It's the standard Bayesian inference algorithm for models with differentiable inputs for a reason. Okay, but for HMC we need the exact gradients at every step, and anyways, we need to calculate the Metropolis Hastings acceptance probability at the end to make HMC really exact. This costs O of n every time, because we need to calculate the neural network prediction for the entire dataset for these two things. In deep learning terms, these things cost one epoch of training. What few people appreciate is that you can also use stochastic gradients, or even the wrong gradients altogether, with HMC. But stochastic gradients make the sampler misbehave, and anyways, you need a Metropolis Hastings step to ensure the result of the algorithm is still correct. Okay, fine, let's try something else. I've heard of this algorithm literally called stochastic gradient HMC. Surely that would work. And indeed, the authors of that paper claim that you don't need a Metropolis Hastings correction with it. Sadly, that's only true if your gradient noise is Gaussian with a known covariance and your step size or learning rate goes to 0 anyways. The latter also makes HMC exact, but you don't see HMC people advocate for removing the Metropolis Hastings correction. Why? Because neither of these two things ever happens in reality. The gradient noise is not Gaussian, sometimes very much so, which can have dire consequences, and the step size never actually reaches 0. So if you gave SGHMC a sample from the posterior, it would spoil it and make it not a sample from the posterior anymore. Okay, fine, maybe we do need a Metropolis Hastings correction. And this is finally what this paper is about. We showed that doing a Metropolis Hastings correction on SGHMC is impossible, because the acceptance probability is 0, with probability 1, no matter how small your step size is. So why does SGHMC have 0 acceptance probability? It comes down to the structure of the Metropolis Hastings correction. For these schemes based on dynamics, we first augment the parameters theta with a vector of momenta m, of the same dimension. Then we make up a target distribution, p bar, that has the posterior as a marginal over the parameters. So then the probability of accepting a new sample S star, given that we started this step on sample Sn, is given here. The important quantity is the ratio of the backwards and forwards transitions on the right. In the SGHMC scheme, the probability of going back to the starting point for the transition, given the next parameter and negated momentum, is always 0. The problem is that the SGHMC step is not symmetric, so a backwards application of the scheme will not retrace its steps, like HMC does. You would think that the Gaussian noise in the scheme, here highlighted in green, would make it so the backwards transition is realizable if you get lucky with the backwards Gaussian sample. But it does not, chiefly because the Gaussian noise is d-dimensional, but the state space of SGHMC is 2D-dimensional, since it has both parameters and momentum. So you cannot make up the error with the backwards Gaussian sample. Okay, what can we do instead? Well, we can use what in this paper we call the gradient-guided Monte Carlo scheme, which has been discovered many times in statistics and molecular dynamics. The name is taken from Horowitz's 1991 paper. GGMC is a simple, time-symmetric integrator for Langevin Dynamics, which are the same dynamics that SGHMC targets. It behaves better than SGHMC when uncorrected, and also accepts Metropolis Hastings corrections. Also, it generalizes HMC and stochastic gradient Langevin dynamics by setting the parameters to different values. To avoid doing a full sweep over the dataset for every iteration, we can delay the acceptance probability using the scheme by Zhang et al. Simply, we multiply the acceptance probabilities of all intermediate steps, and the expensive likelihood terms cancel out, except the first and last one. We can use this to make the Metropolis Hastings acceptance a small overhead, for example of 10%, by calculating it in only one of every 10 epochs. Overall, I think in this paper we have made a compelling case to convince you to stop using SGHMC. GGMC is also simple and behaves much better. There are many different modern schemes that also have these desirable properties and more, which we also list in the paper. Thank you for your attention. Remember to check out the description below for links to the paper, the references, the slides, and soon the code. Thank you.